We're about to start our keynote. We have Colin O'Flynn here. He's come down to help us out. He is the CTO for New AE Technology and a professor at Dalhousie University. And he's here to carry the conference in part. Thank you, Colin.
Thank you so much. Thank you so much for having me here and for organizing this. I know actually we were just involved with the conference in Halifax, and there's a lot of things. I grabbed a water, and I don't want to ask how much they are charging you for every water that gets taken, because there's that. Yeah. Yes, it's a delicious water. So I'm here to talk about, there's kind of two parts to this talk. So it's a bit of a background on the introduction of side channels and the importance of new people coming into research and this kind of transition between academia and industry. The other part of it is a bit of a talk about a newer side channel that came out last year, and then I did some work extending recently at this conference earlier this month, actually. So part of this talk also came about because when I talk to people at these events, they say, like, I've never been involved in this work before, or I've just done a little bit of soldering, or I've never soldered. And they really feel like, I can't contribute, I'm an imposter to this area. And the point of this is that, a lot of people feel that way, but on the other side, I've spent a lot of time now, in academia and industry, helping manage things, not having as much time hands-on, and I feel this way instead. And so I'm not spending all day in the field, I'm not getting that experience that people have, and I don't also have a lot of kind of unique perspectives. And that's what, when you look at the history of these, research and the history of what's come out that's made a big impact, it's often people who are working in, ICS or working in automotive or working in some field, they see an attack and try to apply it, and it's, very successful. All right, so who am I? So this is me 20 years ago. Since then, so this was high school science fair project, I worked a lot of different jobs. So I was doing a lot of embedded system design. As part of that, I worked with Atmel, which led me down a path of working on smart grid and related things. Since then, I co-founded a company that's been acquired by a UK nonprofit dealing with open source security and open source security tooling for hardware embedded systems, and also with the university as an assistant professor. So I've kind of seen a bit of both sides of industry and academia. That's quickly about me, and now I want to talk about side channels. So the idea of side channel is you have sort of a main channel to leak something, which would be just, observing or going through the door, and people say the side channel, they say, well, that's just going through the window. So there's this other way of getting information out that people didn't intend, and it can have amazing impacts on the security of these devices. I'm just going to move this a bit. One example is a timing side channel. So timing side channels were one of the first used for breaking embedded systems. The idea is pretty straightforward. If I had this C code here, right, I have a pin code, 1, 2, 3, 4, 5, 6, and to compare the pin code to what's been entered, I just compare one character at a time, and as soon as there's a wrong value, I return out of this function. The problem with this is the amount of time this function takes will depend on how far in the comparison I got. This isn't just academic, so I looked at some little secure hard drive enclosure. So you put your hard drive in this thing, it has a pin code you put on the front, and you can basically enter your pin code to unlock the hard drive. So their method of comparing did something like this, and so you could basically look at, there's an LED somewhere, I forget where on the board it is, let's pretend it's over here, that gets driven by a signal, and you basically figure out from the time I press the button to the time the LED comes on, I can measure that time and figure out if the last digit I entered was a right or wrong digit, and you can basically measure this timing to kind of brute force the pin. So in this example here, I have two different timings. So I have a time here from the button press to the LED that's a little longer than this one, right? And in this case, the correct first digit is 1. So I entered 066666 or 166666. And the case where the first digit's correct, it takes a little longer for it to put on the fail LED, right? So by observing this timing side channel, we can actually figure out one little bit of information. And the nice thing about this is that we don't have to try every single pin. We just try 0666, 1662, etc. We figure out that digit, and once we know this digit, it's locked in, and then we just apply the same attack sequentially. And so this same sort of attacking a little bit of a system at a time is going to apply to an entirely different side channel. Oh, because there's 1, 2, 3. So this other side channel was one I kind of learned about a bit by accident. And so I was at a conference on smart grids, and there was a speaker there, Paul Kocher, who talked about differential power analysis. So if you don't know about differential power analysis, this is the fact that devices take different amounts of power depending on the data that is being processed, as well as depending on the instructions that are being processed. And so in 1999, he had a paper with 2 other co-authors introducing this field of differential power analysis, and co-founded a company that also protected devices against it. So this is 25 years ago. This area was introduced. And the basic idea here is that inside chips, we have digital lines. These digital lines get driven high or low. And depending on if you're driving them high or low, you basically are charging or discharging a capacitor. And by charging and discharging the capacitor, it actually takes tiny amounts of power. So the crazy thing about this is that there's actually a power difference that depends not only on what a device is doing, but even the data that a device is processing. So it's very powerful because even algorithms that have no timing leakage still leak the data that are being used by them. Okay, so how would you exploit that? So classically what you would do, and so I'm going to do a demo here with a little device I built a while ago that has a small ARM microcontroller. And on this microcontroller, I'm going to run some code. And this code in particular is going to run AES. So it's a very good, encryption algorithm that has no known attacks on it classically. And while that's running, I basically have this resistor here. And this resistor lets me measure power that's being used by the device. And it lets me measure this power on a very, very fine-grained scale. So I can basically measure power on individual clock cycles of the device. And so the other half of this is just measuring that power and sending it back to a computer. You could replace this half here with an oscilloscope or anything else. I've kind of made some special purpose hardware that was part of my original research to make this more recreatable by other researchers and things like that. All right, so physically it'll look like this. So I have this little device here. And this little device has on this side of it that ARM microcontroller. So I've programmed it with an example algorithm, and in real life this would be a separate device, and I'll show some real life examples after this. And then this half of it is actually doing the power measurement. And so we're measuring the power while the device is running, and we're going to be able to use that to do some interesting things. So what that looks like is... so this is running some of this open source chip whisperer tool. Basically, it's been programmed with AES. So this sequence here is the power usage of the device with time on the bottom axis as it's running AES. So if I run code where I have the same data being processed, so I always send it the same data. Oops. Sorry. Come on. There we go. You see some movement, so these changes in the power usage. There's some random changes in it, so it's not a noiseless system. This is real life. But we can see a very defined structure is one thing. So AES has 10 rounds, so we're basically seeing 3 of the rounds here. We can see these 3 patterns that are reoccurring, and those are each part of the rounds of AES. If I look at the same thing and send random data to it, so rather than sending the same data every time I send random data, and I have a better graph after this because it's hard to visually compare it. The spikes are a little bigger here. They're jumping around a little more because the power usage is actually depending a little bit on the data being processed. So if I take those 2 traces I had and basically plot the changing here and the constant here, what you would see if we put them beside each other, which I did on this slide just because it's hard to do it really quickly and not have you go cross-eyed, is that there's a little more variability when you have the changing input data. So in particular, up here at the top, you can see some more variability in the data. And that's because that section of the code actually depends on the data being processed. So there's some algorithms we can use to recover what the secret keys are based on that data. And so this was introduced, as I said, in 1999. I'm showing a slight extension to it here that's from about 2004. But this is all quite well-known topics. And so in this example, what I'm going to do is I run an attack based on those power measurements. And it actually runs so quickly it doesn't seem super believable. Because what you're seeing is that this is each of the bytes of the encryption key. The correct byte I've highlighted in red only because I know what that byte is. And let me restart it. What you'll see is that it actually, at first, doesn't have the full correct key. And after about 50 encryptions it's observed, so here some of these are wrong, it's almost recovered the full key. So it can be a very, very effective tool to break AES implemented on a microcontroller, right? AES just trying to brute force it would be impossible, but doing this simple attack, you can very quickly recover this key. But that's, of course, sort of theoretical. I've programmed the AES, all that stuff. I am using off-the-shelf, implementations, so it's not like this is fake. But how real, if you want to apply this to industry, how would this work? So here's an example from real life. There was work I did in 2017 looking at Philips Hue smart light bulbs. They basically used AES in one of their bootloaders. So in this example, this chip was removed from, and there's more presentation on this, removed from the bulb, put on this device to do power analysis, recover the key for the bootloader, and then recover the firmware for the device. Once you had this key, you could actually reflash the bulbs over the air. And so this was the basis for, one sec, PowerPoint's crashing. This was the basics for this work, which basically showed how you could reflash the bulbs and they could all reflash each other type thing. There's a little demo I did because you didn't want to make this malicious worm where I basically made these annoying light bulbs, I called them, where if you turned one bulb on, they would broadcast a signal and turn each other off around, as well as randomly turning on and off. So if I turn on this bulb, it turns the other one off. And stuff like that. So that was kind of a simple demo that you could really do this. These are sealed bulbs that have been reflashed over the air. There's lots of other real examples of that. So YubiKey most recently has been in the news. It was actually in 2013 there was an attack on YubiKey using side channel attacks. This was attacking AES as part of the usage in 2013. Fast forward 11 years, 2024. If you haven't seen, there's a paper by Ninja Labs published earlier this month looking at a more recent, I think the most recent version of YubiKeys, and basically attacking not AES, but ECDSA signature. But same sort of idea, we can measure the power in different ways, use that to recover secrets that should not be able to be removed from devices. So these are very practical in many situations. But most of this is using older leakages. So what I talked about was using a shunt resistor, where I have a resistor in it. Some of the more recent YubiKey work was using electromagnetic, where we have an electromagnetic probe over the device. There's lots of other ways of measuring leakage. So you can measure just kind of leakage based on power, based on photonics, so based on optical emissions. Capacitor noise is interesting, static power, thermal. So there's all these ways that have come forward. And most recently in 2023, and this is what I'm going to talk about more today, so this is kind of like the more technical part of this talk, measuring the jitter. And I also want to talk about how a simple academic kind of presentation of this can then be turned into a more industry-focused or offensive use case. Okay, so that's just the papers for reference. So photonic, I just picked two that you might not have heard of that can be interesting. So photonic emission, basically the deal here is we have a device mounted. We're observing the emissions from the device. Depending on the data that's being stored, the emissions from the device actually look different. So that's one example of kind of a new side channel. Acoustics is another pretty interesting one. So what you have here is you have a device that's measuring the signals from this target laptop. Why this works is inside of these devices you have capacitors and things, and capacitors are basically plates, metal plates. As these charge and discharge, they make a small amounts of noise. Similarly, you have things in the power supplies called inductors that are coils of wire. These coils of wire, if you heard that whining ever from something charging or something like that, that's often an inductor whining. So they'll make noise that depends on the data being processed potentially, if the data is causing power consumption changes. So there's sort of this leakage where it flows from power into another method, which then flows through to the measurement device. So there's all these new side channels discovered that you might not actually expect unless you went and tested them. Basically, physical properties lead to new leakages. So that's kind of the idea, is if you can think of physical properties, there may actually be new ways of measuring side channels of attacking devices. One of these new methods was called JIT-SCA. So this is work that was published in last year, 2023, at this conference CHES that was just in Halifax. And so it basically looked at what they called jitter-based side channel analysis. The idea of this is that if we have a device that is running some secrets, basically those secrets, just like with this acoustic method, the power usage influences some signal, and we can measure the impact of that signal on a target. What is that signal? What does that impact? Is basically related to jitter. And it's amazing that these new leakage methods are still discovered like 23 years later. And that's kind of the cool thing, is there's still work being done that's quite fundamental to what we understand about how a device is secure and how we can measure this. So as an example, using jitter as a probe, what we have here is this crypto with a secret inside it. We want to get that secret out. This is, for example, a microcontroller or whatever, some silicon device. And basically, as the microcontroller processes this crypto, that power is changing. So this is exactly what I showed, right? These were these signals like here, these power traces. So here I was measuring the power directly. In this jitter case, that changing power is impacting is inserting jitter into these signals. And this works because this changing voltage doesn't just go to like the crypto processor or the microcontroller core or whatever. It goes to the whole fabric, which might include like PLLs and I/O routing and things like that. Why does that actually cause jitter? Basically, as you change voltage, you have changing delay. So as the voltage goes up, the delay time through these digital devices shrinks. As the voltage goes down, the delay increases. This is basically anyone that's overclocking is dealing with this. They're trying to increase the voltage to reduce the delay times. At the same time, they're trying to reduce the temperature, which also isn't a leakage thing we're using right here, but the temperature also has an impact on it. So it's a very fundamental property that's also been well understood. It's not at all unexpected that this changing voltage gives us this jitter. Finally, and sorry, this diagram looks a little crazy, but all it's trying to show is that if we have this changing voltage here, it's also fundamentally changing what the I/O threshold voltage is. So it's basically showing these voltages are changing. This will impact what we call a logic high or logic low, which also introduces delay and jitter. So there's multiple reasons we get this jitter. We don't really care why. All we care is that we have this case where there's a secret running on crypto. This is giving us a signal, and by comparing the original waveform and a waveform that's come out of the device, we can see how much jitter was added, and we can use that to do our power analysis attack. The part about this that's kind of reinventing the wheel that I found interesting is that jitter is just another name for what we would call phase modulation as well. So this is well known in RF and radio. Phase modulation means that, with jitter, we basically have this changing time of when these rising edge occurs, which we could also consider as like a changing phase. So the easiest way to show this is with a simple case where we have one of two valid, what we would call phases. So we can see right here, there's a sudden shift in the phase. The waveform looks like it's flipped. So this is a binary 1 or 0 phase shift, but we can also have an analog, just a kind of shifting phase. It looks a little weird in the time domain, but this is a well-known method of modulating a signal. So it's also not something that's new. So we kind of have this well-known field of differential power analysis combined with a well-known field of RF receiving using phase modulation, and it gives us a very new and unique leakage system. The other interesting thing about this, and why I say if people say, "Ooh, I could never invent something new," it may not even be that you need to invent something. You just need to look back through what was maybe not explored further. So in 2002, there was actually a paper that had a lot of other really good information talking about electromagnetic side channels. As part of that paper, it actually mentioned what they call angle modulation and how this is a really valuable leakage method. So kind of for another 19 years, 23 years, this information was out there, but not fully brought into the scope of very, I don't want to say useful, but sort of a full-blown attack. And so this angle modulation, by the way, this is just talking about like the vector angle, right? So if you use vectors to represent phase, you would have this angle modulation. So that's where the name comes from. So yeah, that's kind of the idea of this new leakage type that was discovered. Now this is more an academic work I want to say. So this JIT SCA work laid the groundwork to prove this is possible and prove it's possible with a device where you have, let me go back to the threat model here, where you have a transmitter sending some data to a receiver. Industry often asks, okay, well, like, what's the practical side of this? So that's the second part I want to talk about, is an example of taking this academic work and showing a more practical consideration for it. So if you're interested, I have more information on a paper here, and there's a GitHub repo with a bunch of links and examples and data and things like that. So those are all available publicly, so don't worry if you want more details than I have time to go into here. And as a really quick aside, what I'm doing here is I'm also going further down the path of using existing technology. And so in this case, I'm using something called a mixer. So mixer and RF take an input signal, and they basically combine it with a local oscillator to give you a signal that is the frequency plus minus RF. So it gives you an addition and subtraction of the frequencies. So this is used all the time in radio receivers. The basic design for FM and a lot of these receivers uses mixers as a key part of this. It's been built in the past with tubes and things like that. So again, this is not a new technology. In our case, we can use these small mixers. We don't need tubes here. There's no point. We're not making a fancy radio to sell. So we use these small surface mount mixers. If you use a mixer and feed in the same frequency, it basically gives you a way to really easily measure the phase. And so how this works is that if I have my target device, so I'm going to recreate the existing work and then show how we could apply it in a more practical way. To recreate the existing work, we basically consider, okay, we take an oscillator, we take the jittery output that has our information, and then we combine that with a cleaned up reference signal. So we basically take our jittery signal here, clean it up, and compare, hey, how much jitter do we think was added by the device compared to a more stable oscillator. And this gives us a really, I want to say, amazingly clean signal. And the interesting thing about this, so this was my test setup here that I brought, but something went wrong in my bag, so I can't run it exactly. But the cool thing is about this is that there's no analog path between my target over here. So this is the target board that's running my crypto, right? It's all digital signals flowing between the two. So this is going to be interesting when we talk about practical considerations, because we don't need an analog probe on our target anymore. The probe is the time measurement of the data that's being leaked. We can even do this over optical. So in this case, there's optical isolators. So the signal can go like here 10 meters, but you could go longer. Again, if there's time information encoded, there's a possibility it's leaking important data that the device is processing. Right, so with that optical example, this figure here is a shunt resistor like that slide I was showing you. So we can see parts of the AES rounds. The same thing measured over an optical link where I'm purely looking at the time delay or phase looks very similar. And if you do the attack on this, it takes about 2 times more power traces. So not a huge difference, right? If it takes 100, now it's taking 300. In my case, it took like 900, so it takes 3,000. So it means it's still a very kind of in-scope sort of threat model. And this is cool because when you think about the threat models here, there's a lot of attacks in industry where, it's a very academic attack. Is someone going to, so going back to my Philips Hue work I did, do, where is that? I should have put a slide in with this, right? So I made a custom board, took a ton of effort to make this target, to do my measurements, make them very low noise. If all I need is digital, right, you could look at things like ECU tuners where they've basically said, hey, we've made this box that does the magic, just plug it into an existing connector. Plug it into a clock, you pin, right? There's lots of times where they say you solder some wires on or things like that. It's very, normal for this sort of attack model. The other interesting thing is something like an SD card, right? So almost all, I don't want to say all, but a lot of IoT devices have some sort of micro SD card in here. And this SD card is normally routed right to the system on a chip. Part of the SD signaling includes a clock coming out of it. And you might say, well, okay, but that clock is only accessing while you're accessing data. But the nice thing is that if you look at the typical implementation from an SD host, you often have something like this where there's a big loop here. So you can see this well one. And there's basically what it's doing is it's checking if the SD card is busy or not, and if it's not busy, it just keeps retrying. So eventually it times out on this retry, right? But if you were a malicious attacker, your attacker can very easily say, I'm busy, please keep trying. And this is going to turn on a clock, and that clock is going to, of course, encode any jitter related to crypto or something else this guy is doing. So it's, very practical in many situations to get this type of data out of a device. And this is from a Raspberry Pi driver, but you'll see similar stuff in other drivers. Okay, so this sounds cool. This sounds like great. New attack, we're going to make an SD card reader or something like that. But it kind of gets better because this new attack we can also use our old friend JTAG for. And I say our old friend JTAG because if you're doing any embedded hardware hacking stuff, JTAG is coming up all the time. So in 2014, and a little before, Joe Grand had a project called JTAGulator, which made it even easier to use. But well before that, there's been a lot of information about JTAG, getting JTAG ports, getting access, dumping memory, all this stuff. So it's also kind of amazing that we have this interface that's been well known from attackers and from a security perspective, and there's an entirely new threat model that we now may be able to, run, or a new attack we might be able to run on this thing. And so JTAG is used a lot. So I have to push my book. If you write a book, then you have to somehow include it in things. So here I'm searching JTAG. If not, I might be like, hey, that table leg is about 1 inch too short. You could fit a book under it. But yeah, so we mentioned it 130 times in this book. It's a very common hardware hacking attack vector. And how it works, you don't actually care how it works. What you care about is you basically have a few signals. You have test data in here. You have data out. And it's basically a big shift register. You shift data through it. And there's different modes that the JTAG can be in, which is these test access port stuff here. And there's different registers you can use. There's one register called bypass, which is basically a single bit that connects the input to the output. And so you connect the input to the output through this register. What you realize is that this register, right, is sitting on the same power as everything else, the same power as the whole chip. So you can, in fact, feed a clock through this path here and use this as your measurement device on the chip. So now you have a way using JTAG to perform this phase measurement. And what this looks like here is I have a target device, and I basically have some minor special equipment that sends a clock in and then compares the output clock to measure the phase at the output here. And so we now have an equipment that can give us this phase information, again, using only sort of the JTAG port. So we've gone away from needing a whole side channel setup to just potentially needing just JTAG. So electrically, and I'm kind of using the same setup here so that I can more specifically compare between side channel with a resistor and my JTAG setup. But this target here would basically be your target board. And so I have a standard JTAG header on it, this standard 20-pin header that's used on a lot of ARM devices. And again, there's no analog paths here. So this is all digital signals flowing. So I don't have any analog probe, EM probes, anything like that measuring it. It's all digital JTAG signals. And then this board here is doing the mixing to compare some of the clocks to give me my phase output. And so with this phase output, this is how we're able to do our side channel measurement. So similarly, it looks, shockingly similar. So this is V change here is with a shunt. So this would be your classic 1999 DPA attack. And then phase change is our digital measurement. And so you can see visually these look very similar. These are averaged to reduce noise. But you can see, right, we have the same sort of patterns, all this, we have some like spikes here, 3 spikes here, stuff like that. So it looks like a very, very similar attack. And it works. So these graphs I didn't show before, but if you look at any power analysis papers, what these are showing you is what the correlation, which is those red bytes, where I was saying we know the key bytes, it basically ranks it by how well correlated they become. So these red going higher indicates that the attack is succeeding, and it succeeds at a reasonably high rate. Takes like 5 to 9 times as many power traces as a best case shunt resistor, but again, without any analog connections, with purely digital connections. So yeah, so it's pretty amazing that it's able to work so well and provide this this attack. Okay, so the other thing is it gets us slightly better too. So right now, I needed feedback from the device where I'm measuring the phase. There's another attack vector using JTAG or using other digital signals effectively, but JTAG's one I'm looking at here, where what we do is, so this is a flip-flop and really anything inside the digital device. This flip-flop typically has 2 signals, so it has a clock signal in here, and it has a data signal in here. So any device will have these 2, data and clock signals. JTAG is nice because we control the clock and data signals, so it's a bit unique that way. And so what we were doing before is I was measuring the phase information at the output here. So we were inserting some jitter into one of these signals. I was measuring at the output. What's the difference in phase between this input signal here and this output signal, right? And this is the measurement. Let me delete my flip-flop arrow. Right, so that's the phase difference, is between the input and output, so that's what's related to the power consumption from the device. What we can also do is take advantage of the fact that the flip-flop itself has this probability of what data is getting latched in. And this probability, if I imagine that I kind of clock the clock and data in at about the same time, if there's a small variation in when this data edge happens, right, this data edge could be over here. So if I slow down my data edge, it could be right over here. So flip-flops typically have a spec, or digital devices have a spec, of how close you can change the clock and the data. If we purposely violate that, what it means is that we can now be in a situation where either a 1 or a 0 could be clocked in. And so there's a second way of doing this measurement, which is just subtly different, in that I don't have my phase measurement. Instead, what I look at is if I got 1 or 0s out. This is interesting because I don't need any precise digital timing information. So you can also imagine situations where you don't have the ability to very precisely measure the phase output. So what if you had the situation where you don't have precise phase measurement, but you can see if there's a 1 or a 0? So here what I've done is I've connected the output to just a logic analyzer that just records 1 or 0, doesn't record what this precise phase measurement was. It looks a bit different because I no longer have those nice power traces directly. What I have is a result of just 1s or 0s over time. If there's no faults in here, it should be a constant value. But what I've done is, because I've biased it right around the point where the device is operating or not, or clocking in the correct data or not, as the power changes, it becomes more or less likely that it flips the bit effectively. So because I have this right on the edge, if the power dips, right, or spikes, if it dips, the delay becomes longer. If it spikes, the delay becomes shorter. So it becomes more or less likely that I clock in a 1 or a 0. And this is basically what I do here, is I record a whole bunch of them, and if I average them, so in this case you see I averaged a lot of them, I get something that also looks like a power trace, but with only measuring a 1 or a 0. So I've thrown away all of the very fine-grained phase information and just measured a 1 or a 0, and I still get power trace-looking results. And you're still able to do this attack. It takes more traces, so if we look at how much data it takes to do this, it takes a bit more data, which you kind of expect, but it still works. And so that's also interesting, that there's multiple ways to use what was this reasonably straightforward academic result about jitter being potentially leaky, or not potentially, but is a leaky way of observing these power traces. And you can actually attack the trustworthy JTAG interface about 2 or 3 different ways with this information. The other kind of cool thing is that because JTAG operates separately from the device cores, here I have a bunch of different microcontrollers. So for example, I did most of the work on this first one. That device is spec'd to operate at up to 120 megahertz. So the core frequency is good to 120 megahertz. But the JTAG itself can run faster. So on most of these devices, the JTAG block is a separate block. It's not clocked from the core or anything like that. It's used for debug. There's reasons that it's separate like this. As a result of that, though, you can use the JTAG as a very high-speed interface. So one of the other points is that if people are designing these systems, there's certain devices where you can disable the JTAG and certain devices where you just cannot fully disable the JTAG. It's not even possible. So these devices have no way to kind of prevent this from happening if they expose the JTAG port, which most devices will for programming and debug and things like that. So for these devices, it's very, very difficult to protect against these sort of attacks. Which again, this is interesting because power analysis was published in 1999. The phase angle modulation was 2002, and it's kind of sat there as a threat that wasn't fully exploited for many, many years. So yeah, that's kind of the big points of this talk. So I wanted to leave some time for questions, potentially more demos, but really it's that, you know, things can be around for many, many years and still have new discoveries. And the example I'm using here is measuring jitter. So jitter measurement is something that I think is going to be built on in the coming years. As I said, the initial work in 2002 published about this. Nobody really picked it up as a, you know, full example until last year with the JIT SCA work. And then I'm trying to show here that you can also do this on other interfaces like JTAG, and it works extremely well. If you're interested in this, all of the design files, notebooks, and things like that are available on this GitHub repo. And if you want to reach me, I'm no longer active on Twitter, unfortunately, but these are kind of some of the sites, and I'll eventually post this, these talk slides on my personal website. I'm not sure if they're being posted online too, but welcome to have that. So thanks very much, and I guess if there's any questions, I can take now. Yeah.
So they will be posted online.
Okay.
But quick question. So you showed in the devices that you showed, you said that the jitter attacks, here specifically. So on NPC 5777C, we have the rare example of the core frequency being higher than that of what the JTAG is capable of. If you were to run this attack on that device, would you have to force that core frequency lower than the JTAG frequency, or is it not really as viable of an attack because of the sample rates?
Yeah, no, that's a good question. So it would depend a bit on what you're attacking. And so, yeah, so this device here, for some algorithms, like asymmetric algorithms, it doesn't matter at all. So that was like the work on acoustic attacks here. Where was that? This example, so in this case, right, the attack channel, it's like kilohertz because you're acoustic, and the core is gigahertz or something like that. But it's running a very slow algorithm, so it doesn't actually need super fine-grained information. If you had the case where you're like a hardware AES, it might be problematic because the device is running so fast. You can't get the sample rate up. But yeah, so it would depend a bit, but. And I don't know if these were optimal. These were kind of a quick, like, let's, see how quickly I can get it to run without doing a lot of delay, matching or things like that. So it might be possible it's faster, but it may also be that that's just the limit. I also have here, so what I didn't mention is they spec how fast the JTAG interface should run, right? And so you can see for this device, they only guarantee it up to 10 megahertz. So it may just fall apart because it was never designed to run even close to this fast. And this disparity is because I'm really using the this single bit path. I'm not using all the fancy stuff up here, right? So this probably will fall apart at a lower frequency, but all I care about is this one path that's really simple, and that seems to work at higher frequencies.
Are there any differences against these kinds of side channel attacks?
So in general, yes. So the side channel attacks, you basically have this. If I go back to where's a good one? Sorry, I'm trying to find a more useful slide. Yeah. So basically, this is a good example. So this changing input data versus constant input data. The way the attacks work is they basically rely on knowledge of, you know what, I have a better slide I can pull up. This was a different talk, but this is kind of what it looks like. So they rely heavily on knowledge of the input data here, which is assumed like that's not a, it's the ciphertext or something like that, and measuring the power. And you basically have a model of the system. In this case, let's just say it's a simple XOR, and you can basically use your model of the system with a model of how it leaks to figure out what the most likely secret key is. So there's a number of techniques to protect this algorithmically. The simplest is something called masking, where if you imagined you just put in a random number here, and then you take that same random number and XOR it, and obviously there's some changes to the algorithm needed if this is more complex, but as an attacker, I no longer know I no longer have the full picture of what's going into the algorithm. So if I build my model, it's not going to be accurate anymore. So there's this technique called masking, which very fundamentally protects against these side channel attacks. So, in this case, my changing versus constant input data would not look so obvious because in both cases, the algorithm's processing random data. So if you mask the actual implementation and it doesn't leak for power analysis, then this phase modulation would also be irrelevant. So it's more a new way of doing measurement. So if you protect against the old measurement technique, it'll work against this too.
Do you not use the same analysis to kind of pick up the random number?
Yes. So this is where it goes. So it becomes more complicated because then you have this attack to figure out the random number and stuff like that. But what we would call the first order attack, where you just do the kind of blind dumb thing that I've done here, would fail. So I don't know the.
This could work on like campus.
Maybe. So that's one of the points is there's a lot of these interfaces on things, and so anything with relatively good timing may work quite well. So I've never tried it. This is just things I've tried very recently. Really, the only restriction is that as long as the data is being generated on the microcontroller that's processing something interesting, then it should be good. Like, it doesn't matter if there's, I had my optical isolators, if there's transceivers in the way, they should just pass the jitter through from the original device. So it should, but question in the back.
If I remember correctly, jitter is affect the voltage variation. So why would I ever use this in power analysis?
Why would you use this instead of power analysis?
It's a downstream effect of the power.
Exactly. So the only reason this would be more relevant is basically because it's accessible. So the idea of this is that with power analysis, I had access to. Sorry, I'm trying to find where's my little slide. Right, with power analysis, I either took the device out and put a shunt resistor in or modify it. In some of these real life examples, they have an EM probe on the device. So one of the points of this sort of attack is that, I think it was after this. Yeah, is that you don't actually have to modify the hardware target that much. So rather than having to say, okay, you need to use an XYZ table, an EM probe, or modify the PCB, you may be able to just plug into the existing JTAG header. So in terms of product sizing it, it's a bigger threat because you don't have to have someone who does the effort of taking the device off. The reason that becomes kind of interesting is a lot of manufacturers have moved to unique keys. So for the Philips Hue example, that worked because they had the exact same shared key in every light bulb that was produced. So once we used power analysis with great effort and destroyed several devices, that was fine. We could destroy as many as we needed because that key was good. More recent devices don't do that. So if you destroy the device, they don't care because that key was only used one time. If you have a way to do the attack, relatively low cost, relatively quickly, without destroying the device, there's a lot of kind of threat models it breaks, right? Or in this example with an SD card slot or something, where there's an allowed security boundary where they say, okay, the SD card slot is, like the case is tamper resistant, but the SD card slot or the smart card slot or some slot is actually a fine thing for a user to do. It becomes a kind of interesting threat model. But the leakage is worse. So that was kind of also the point of the paper. It is worse than just a pure shunt. So if you do the shunt, this would be silly, right? But if you can't do the shunt, this could be interesting. All right, thank you very much.